Welcome back. This is Mr. Hassan's Maths channel, and I'm now answering question number 6 from the October-November 2004 Pure Mathematics P3 paper from Cambridge 9709. And this question is also question number 1 from my end of topic worksheet number 14, which is about complex numbers. And this is a topic which is not in Edexcel A-level maths. It's in further maths for Edexcel, but for Cambridge it is in the A-level maths. So this is probably one of the first videos I'm doing on complex numbers, because I'm to now really only been doing Edexcel A-level maths papers, but as I'm now teaching Cambridge in my school, I'm going to also be dealing with the Cambridge papers as well for A-level. So this question here, we're told about these complex numbers. 1 plus 3i and 4 plus 2i are denoted by u and v respectively. So basically, they told us the complex number u is 1 plus 3i, and the complex number v is equal to 4 plus 2i. So it says find in the form of x plus iy, where x and y are real, the complex numbers u minus v and u divided by v. So basically, a complex number is a number that is made up of two parts. You have a real part, all right? So you have a complex number, z equals, you can say a plus bi, where a and b are real numbers, okay? So you have the real part of the complex number. The real part of the complex number is, in this case, it's going to be your a, and you have what's called the imaginary part of your complex number, which in this case is going to be b. Okay, so the I stands for basically the square root of -1. When you get to a question, before we learned about complex numbers, you had a question which you end up with a square root of a negative number. We say it has no real solutions, right? It has no real solutions because you cannot find the square root of a negative number, because two numbers multiplied together to give you a negative number, well, they have to have the same sign. So by definition, you can't have two numbers with the same sign giving you with different signs, giving you a product that's negative. If they have the same sign, they're going to give you a positive product. All right. So in real numbers, in the realm of real numbers, such a thing doesn't exist. So we say there's no real solution. But to get around that, the mathematicians have, basically come up with this system of what are called imaginary numbers. And, basically the square root of -1 is the definition of the imaginary number. So we can say I squared is equal to -1. Okay, so the value of I squared is -1. And you'll realize that this imaginary number system actually goes a long way to solve lots of problems. And it's been used a lot in, different types of technologies and so on. So it's not just something that's like some abstract, weird kind of idea. It's something that actually does have some practical uses in, real life, in terms of, solving some real problems, especially in the fields of electronics and stuff. So it is not something just a bit of a plaything for mathematicians. Anyway, that's besides the point. We're going to learn how to answer this question. So now, you have here imaginary numbers are made up of a real and imaginary part. So it splits up into these two parts. Okay, so now in terms of answering this question, it's pretty simple. It's just basically the first part is just subtracting these two. So if you want to find what u minus v is, you just subtract these two from each other. So you have 1 minus 4. So you have the real part will be 1 minus 4. And then you have the imaginary part is going to be 3i minus 2i. You're just subtracting them. So u minus v is going to give you -3 plus I. So that's the answer for u minus v. Simple as that. Okay, so that's in the simplest form, u minus v. And then we'll have to find u divided by v. Now u divided by v will be basically 1 plus 3i over 4 plus 2i. Now, to express this in its simplest form, it means basically in the form x plus iy. That means in its simplest form. Now what we have to do is we have to do something very similar to when we rationalize denominators. Here we have a denominator which is imaginary. It's made up of a complex, it's a complex number made up of a real and imaginary part. So what we have to do is we have to make the denominator into a complete number which is completely real. So we have to basically, it's called realizing the denominator. Not rationalizing, but realizing, making it into a real number. So what we're going to do is very similar to what we did with imaginary number, with irrational numbers. We're going to multiply it by its conjugate. So 4 plus 2i, if you multiply it by 4 minus 2i, it's like you're kind of applying difference of squares, and the middle term, which will be the I term, will disappear, cancel out, right, as you will see. But if I multiply the denominator by something, I must multiply the numerator by exactly the same thing, such that I have not changed the value of the fraction. So I multiply the denominator by 4 minus 2i. Why? Because it's it's the conjugate of this. It will get rid of the imaginary number part. And I have to multiply the numerator by the same thing. Otherwise, it won't be the same fraction. So if I deal with the numerator, I have 1 times 4, which is 4. And 1 times minus 2i, which is negative 2i. And 3i times 4, which is plus 12i. And 3i times minus 6 times minus 2i, that's going to be negative 6i squared. Negative 6i squared. And the denominator, okay, so basically what you're going to get here is you're going to have 4 times 4, which is 16. You're going to have minus, you're going to have 2i times minus 2i, is going to be basically minus 4i squared. Where did the middle term go? Well, I mean, all you have to do is basically square the first number and square the second number and subtract them. Okay, why? Because you have a difference of 2 squares. As we'll see, if I do the long way, I'll show you over here. You're going to have 16, 4 times 4, and you have minus 8i, and you have plus 8i, and then you have minus 4i squared. So these two cancel out. So you just have with 16 minus 4i squared. So when you see something like this, a difference of squares, you just square the first number and take away the square of the second number. So 2i times 2i all squared is 4i squared. Okay, so now we can use the fact that we know that I squared is equal to negative 1, and we can replace all the I squareds here with negative 1. So you're going to end up with 4. This is minus 2i plus 12i, which is plus 10i, and you'll have minus 6 times negative 1 over, and you'll have 16 minus 4 times negative 1. So I've replaced the I squareds with negative 1s. So this is going to be 4 plus 6, which is 10, plus 10i over, and you have 16 plus 4, which is 20. So if we realize we have a common factor here of 10, so let me just put this a bit lower down. So we have a common factor here of 10 in both the numerator and denominator. You take the 10 out, you have 1 plus I over, this will be 20 here, they cancel out, and you're left with a half plus a half I. So we can say that U over V is equal to a half plus a half I. Okay, then it says part 2, state the argument of U over V. Right, so I'm going to draw a diagram, although we don't need to draw a diagram, just to make you realize what we're doing, right? What the argument means. Okay, so here we have these two axes. Okay, so this is called the real axis. This is the real part of the Z, the complex number, and this is the imaginary axis. So this is the imaginary part of the real number, of the complex number. Okay, so the imaginary part and the real part, you can basically, the x-axis is the real part and the y-axis is the imaginary part. So if you have your complex number a plus bi, you can actually plot it like a coordinate. So for example, if this is a and this is b, okay, then you can plot a line. You can plot the point here, and you can have a line that joins a point. So this is basically the point AB, and this would be the complex number Z. That's how you can illustrate it as a a line in this coordinate axis, imaginary number and real number. Okay, so you can represent every complex number on this pair of axes. Okay, now the argument of a complex number, the argument of the complex number z here, is basically the angle it makes with the real axis. Okay, let's call this, for example, theta. This is basically the argument of a complex number, and the value of the angle should be between 0 and we normally use in terms of pi, between 0 and pi. Okay, so basically, it's basically going to be between minus pi and pi, right? So the argument, if it's on this side, if it's a clockwise angle, if it's an anti-clockwise angle, if it's somewhere over here, the argument will always be between 0 and pi. If it's down here, we normally give it in terms of between 0 and negative pi. That's the normal format. Okay, so the argument of z would be basically this angle, and this angle is found by using the tangent. So this side is your b, this side is your a. So we can say that the tangent of theta is b over a, right? So we can say that the argument of z would be inverse tan of b over a. Okay, so if we take our complex number u over v, we worked out to be a half plus a half I. We worked that out in part A. All right, so if you want to find the argument of u over v, the argument of u over v, then it's going to be basically inverse tan of b. Now this is your a part, this is your b part. It's going to be over half divided by half, which is equal to the inverse tan of 1. All right, and we know that the inverse tan of 1 is pi over 4. Pi over 4. So we can say the argument of u over v is equal to pi over 4, 45 degrees. There's the answer to part 2. So we don't have to draw this diagram. I'm just illustrating what the argument of a complex number actually means. It's the angle it's making with the positive real axis. Okay? That's what the argument of a complex number actually means. All right, so that's the answer. And there's also something else which you haven't got in this question, the modulus. The modulus of a complex number is basically the length of this line. So it's found by Pythagoras' theorem. They said find the modulus of this. We would just find, a squared plus b squared and square rooted. That's the modulus of a complex number, the length of this line that when you draw it in the plane, what its length is going to be. All right, but that's not even asked in this question, but just a little side point. Okay, now, so that's part 2. And some kind of more understanding of this is going to be shown in the subsequent part of this question. So I won't go into that right now. I'll go into that when we get to it in this latter part of this question. So now for part 3, it says, in an Argand diagram with origin O, the points A, B, and C represent the numbers u, v, and u minus v, okay, respectively. State fully the geometric relationship between OC and BA. Okay, so basically that's what this is called, which I failed to mention. This is called an Argand diagram. When you have these pair of axes, that's actually the proper name for this, Argand diagram. Okay, this is called an Argand diagram. All right, so what we're going to do now is we're going to draw one for these actual complex numbers that we're given. So it says, with origin O, represent the numbers u, v, and u minus v, respectively. So I'm going to draw my pair of axes. Let me just do that a bit better. So we'll draw my pair of axes. I don't see I have to go to the negative side, so I'll leave it like, I'll just draw them this way. Okay, so here we have our real part of the imaginary number. Here we have the imaginary part, of the real part of the complex number. Here we have the imaginary part of the complex number. And this is our origin, this is O. So if we represent u, it's going to be 1 plus 3i. So 1 plus 3i, let's just put it over here. I'm not doing it to scale. Okay, so let's say that's 1 and that's 3. It's just a sketch, so we don't have to worry. So remember, the complex number is represented by a straight line. Okay. And that's from the origin here. So that's the complex number. This is the complex number u. 1 plus 3i. And that leads us to the point A. And then we have the complex number v, which is 4 plus 2i. So 4 plus 2i. So it's going to be somewhere over here. I'm not drawing it to scale. That's the point B. Say that's 4. And say that's 2. Just roughly. Okay. So now we're going to draw the line between O and B. And that would be the complex number V. Right? And now we're going to represent U minus V. Now U minus V, okay, is minus 3 plus I. Now one way of making this a bit accurate is U minus V is the same as saying, minus V plus U. So it's basically the same as going from B to A here. That's like U minus V, okay? It's like basically, if you think about this as minus V plus U, minus V plus U is the same as U minus V. So this vector here, or this line here, if I just draw it on this side, if I put it on this side, that will be like going, this one here. This is the same as what we're looking for. This is like U minus V. This is U minus V. That's a vector V. This is the vector. You can think of this as the vector U minus V. So if we start from the origin, it's going to be over here. That's going to give us the exact length that we need. Okay, so this is, as you can see, negative 3 and 1. So this is the vector, or this is the complex number U minus V from there to there. Okay, so we have the point C over here. Okay, and we have now drawn those diagrams. Okay, so that's done. We've drawn those three. Okay, and then it says state fully the geometric relationship between OC and BA. So OC and BA, I've just basically shown you when I moved it along that they're basically the same length and parallel to each other. Okay, if I join together B and A, it's exactly the same thing as O to C. Okay, so exactly, you can see minus 3 and plus 1. From 4 to 1 is minus 3 plus 1 minus 3 plus 1. So B to A, okay, so OC is, the magnitude of OC is the same as the magnitude of BA. And we can also say the OC, the vector O to C is the same as the vector B to A. So basically we can say that they are parallel. So we can say OC and BA are parallel and equal in length. They're basically opposite sides of a parallelogram, as you can see, equal in length. Okay, so that's the geometric relationship between them. All right, so there's the answer to part 3. And then it says part 4, it says prove that angle AOB, which is this angle over here, AOB, this angle here, is pi over 4 radians. Okay, so basically what we can see is that angle AOB is like the angle, let me change the color of the pen. AOB is like the angle from the real axis, okay, to OA, and this angle subtracted. So basically the angle here is basically the argument of U. And this angle here is basically the argument of V, because the angle from the positive real axis. So I can say AOB is equal to the argument of U minus the argument of V, right? The argument of U minus the argument of V, right? And it's basically this, as we'll learn probably in some other videos, is the same as the argument of u over v, as we'll see. And we already found what u over v is, but we'll prove it from this. The argument of u, let's see, u is equal to 1 plus 3i. U is equal to 1 plus 3i, and v was equal to 4 plus 2i. 4 plus 2i. So the argument of u is going to be the inverse tan of 3 over 1. Minus the argument of v is going to be the inverse tan of 2 over 4. As you can see, this angle here is 3, the whole angle. It's like this, using this big triangle here. You have a triangle that looks like this. Okay, this angle here is basically the argument of u, which is 3 over 1, inverse tan of 3 over 1. And this angle here, you have your triangle that looks like that. And this is going to be, this is 4 over, and this is 2. Yeah, this is 2, this is 4. So 4 over 2, sorry, the other way around, 2 over, this is going to be 2. So you're going to have, it's going to be 2 over 4. Inverse tan of 2 over 4, which is a half. Okay, which as we see there. So that will give us our angle AOB. So if we take the calculator and we do inverse tan, and we make sure we're in radian mode here. We should always give these answers in radians when we're dealing with complex numbers and arguments. So we got radian mode. If you're not sure, shift menu 2 angle unit and 2 radian. Okay, so we have inverse tan of 3 over 1, which is inverse tan of 3, minus the inverse tan of 2 over 4, which is the same as half. Okay, and that gives us, as we see, pi over 4. Okay, that's going to be pi over 4 radians. So there we have the answer. We've shown that AOB is equal to pi over 4. Right, and if we go back to what we learnt in part 2 of the question, we found that the argument of u over v was also pi over 4. Okay, so this is something that we're kind of proving this relationship, that the argument of u over v is the same as the argument of u minus the argument of v. Okay, so we just kind of proved that by doing this part of the question. Okay, because the argument of u of v was pi over 4, and the argument of u minus the argument of v is also pi over 4, as we can see from this diagram. Right, so there's the answer to question number 4. And that concludes this question from the October-November 2004 paper, and from this question number 1 from my end of topic worksheet from my P3 complex number worksheet number 14. Other questions from this paper, you can find them in the playlist at the top of the page. Other questions from this worksheet you'll find in the playlist over here at the bottom of the page. And on this side, you'll have other questions that I have answered or that I will answer eventually, a playlist for those complex numbers questions from P3. And you can subscribe to my channel by clicking on this link. Thank you for watching and see you soon.